All right, let's do this. I'm recording now. Fantastic. Hello. How's it going? Life's good. So basically, this is a lecture, as Dr. Nee has kind of said, that is beyond AP Computer Science. And the first thing I want to start with, first off, is, let's see. What do you guys remember? What do you guys remember about computer science? What do you guys remember about, these are all things that should have been on your AP test, ideally. Is there anything here that you guys don't understand or don't get?
Exceptions and the generics. I don't remember that.
Exceptions and generics. Okay, cool. That's what most people have said. I think 1 through 7 or 8, 7-ish, you kind of understand 1 through 7 very well. Like inheritance, it's a class, another class can inherit that class, right? Recursion, how do we feel on recursion? Good.
I remember it, but it was not fun.
It's not fun. In essence, yes. Basically, recursion, it's something ideally I'm probably going to go over more, just in the concepts that we're talking about. And if you guys can understand recursion really, really well, that is like fantastic. That is my goal. And that's one of the big concepts in that if you go to college and you understand recursion, you're going to be way ahead of other people. And that once those people get to recursion, they're going to be where you're at right now, where they're stuck for weeks on end, but they only have 1 week to do it. So if you go to college for computer science, and that's up to you guys, that's one of the big topics that's hard to comprehend and understand. But I'm hopefully going to walk you through processes to get there. Hello.
Hi.
We're missing one.
Oh, yeah. Oh, Charlotte?
Yeah.
All right.
Not here today.
Must be out.
You need to go right now?
Yeah, fine.
Okay, we'll just keep talking about this for a little bit. Hopefully you get back in time, I believe. Exceptions. So you guys said exceptions. Any of you know what an exception is?
I mean, I did it in Python, but I don't think we went over exceptions.
Same as well?
I remember particularly the arithmetic exception.
Arithmetic exception?
Related to division by
Okay.
0.
What do you remember exceptions being? In Python, sure.
I don't think we went over exceptions when I was in AP, but are exceptions, are they the like tries in Python?
Yeah, try-catch loops, right?
Huh?
Try-catches?
Yeah.
Yeah, try-catch statements. So basically, if, say, during compiling, you compile perfectly fine. You don't have any errors. Say during runtime, you have an error, and some error happens. Say like, oh, I've gone out of bounds, or oh, I have some different error happens. You can have this exception, which is a try loop, where it says, hey, if this error happens, do this little bracket of if statement, basically. So if this happens, do this section, and then it'll catch the error itself. So that's what exceptions are, in that you're catching problems, you're catching errors during runtime. Searching and sorting, I'm sure you guys have kind of done. We're going to actually talk about that a lot more today, and it'll be the majority of what we talk about in the future. 2D arrays, how do we feel with that?
It's good.
Good. We know how to iterate through 2D arrays.
Sorry.
So, okay, cool. Array lists.
Yeah.
Yeah. Do we know? So we know the difference between arrays and array lists. Do we know why array lists are how they are, in that memory-wise how they work?
It's a class.
It is a class,
They
but
take a lot more memory now.
do they?
Pretty sure they don't have a set size.
They don't have a set size. They can take a lot more memory, but arrays can take the exact same amount of memory, right? So I'll talk about that in hopefully future classes, but it's kind of an interesting topic, how array lists actually work and how things work like that. Graphics you did all of last year. Do you guys know what generics are?
No.
No clue? Generics are, they're generic in that, remember how you guys made an object class, and then you guys made a rectangle and a circle class. And those things inherited object.
Yeah.
But you could create an object, and you could make it equal to a square, a rectangle, or a circle, right?
Yeah.
You can make an object equal to these things, and that's a generic, where objects are generic items that you can kind of use. Similar to how you can use vars or variables. Vars can be integers, doubles, different things, right? It's not necessarily a actual like data type.
So is this like it's like, for an example, like it can be, instead of object, I would say like automobile, and then automobile whatever equals new car. Let's say
Can be.
cars in that class.
Yeah, it can be something like that. So you have a generic class. It's kind of like inheritance, but you can create these things and use them as classes. So that's what generics kind of are. Cool? Alright. So that's what last year was. Now, I want to kind of emphasize that last year was fundamentals of what computer science is. So it's fundamentals in that you're taking code, you're understanding how to learn how to do code. You understand different data types like strings, integers, doubles, all that type of stuff. You understand if statements, input, output, while loops, arrays, array lists, different things like that. So now you know the fundamentals of how to code, right? This next course, that's the first course in college. This is the next course in college, and that now we're taking that stuff and we're kind of understanding how it works. And that this is called data structures and algorithms, and that's kind of what I'm going to be teaching here. And that we're going to be learning a lot of different data structures. What are the 2 data structures we know right now? Any ideas? When I mean data structures, any idea of just what is a data structure? What is a data type? What is an example of a data type? Int. What is a data structure? A collection of integers, or something like that, right? So what is a collection of integers? An array. Array is one of them. What's the other one? An array list. So data structures, we're learning more about different type of data structures in that array lists and arrays are different data structures. Welcome back, yay. We just talked about last year's stuff, nothing crazy. Exceptions are if we have an error, an exception catches it. Generics are, you create an object has a rectangle and circle inside of it, and that inherit it. You can create an object that equals a square, or a rectangle. And that's how you create a generic. But upcoming material, we're going to be learning a lot of new data types. So we're going to be learning lists, stacks, queues, hash tables. Pointers are how array lists actually work. Trees, balance trees, heaps and trees, graphs, algorithms, all these different types of stuff. So these are all different types of data structures. And we'll also learn the algorithms to how to search through them and sort them. And that we have now a giant list of these different data structures. When do we use these things? When do I use an array? When do I use an array list? You kind of understand how to do those two. Now adding all these on, when do we use different things? And the big thing for me is in trying to understand when you use things and why you use things. Because right now for the labs, so far in class, you've kind of done stuff because you've been told to use it, right? Been told to use quicksort, or you've been told to use bubble sort, right? You guys have used bubble sort for the CDs-RS? Was last year? Were you guys last year? Who did last year? Who did AP 2 years ago? Peter? Okay. So then you did Happy Birthday Lab, and you guys did CDs-RS, right?
Yeah.
And you guys probably did bubble sort on that, or some type of sorting algorithm to sort it, right?
Yeah.
So understanding when to use which sorting algorithm and why. And I'm going to go over that today. So these are all cool things. Feel free to ask questions anytime. If I'm talking too fast.
You have to take notes.
No. I mean, it's for you. You're welcome to. I know some people have. But I will post the slides so you guys can have them all. But does anyone know what big O notation is? Yeah. Okay, what do you think? What do you think it is?
It's like time.
Time.
Yeah.
What is
Isn't it like
more than that?
processing speed?
Kind of processing speed, yeah.
Fast.
So same thing in that big O is taking we're trying to figure out how fast our program runs, how efficient our program is. And it's a good indication of how efficient our program is. So the story I like to tell is the pigeons versus the internet. So back in 2009, there was a company in Africa that had 2 branches that are a little bit apart. There was one company branch over here and one other branch over here. Now, in that one branch, they were like, hey, I need to transfer all this data over. Have you heard this before?
Yeah, IP over pigeon, right?
Yeah, exactly. And that there was basically all this data that had to transfer one place to another place. And they're transferring over the internet, and they're like, this is so slow. This is so slow. And they basically, instead of just doing it over the internet, they wanted to test it. That they take a pigeon and they strap a bunch of USB sticks to it, and they fly it from one branch to the other. And the reason why this story still lives is that that pigeon won. So that pigeon won, but it's an interesting concept in that that pigeon had thousands of gigabytes of data on it and was able to get it over in X amount of time. And I'll show you in the next slide. In that, for the pigeon, it can carry as much data as you want, but it'll always finish in 60 minutes because it has to fly one distance. Now for internet, depending on how much data we have, you have more time spending, right? So you're spending 30 minutes on 1 gigabyte of data. You spend another 1 gigabyte, it's another 30 minutes. And as soon as you get over 2 gigabytes, your pigeon's gonna be the exact same amount of time. But your pigeon can kind of keep doing more data. So this is the concept of, this is a linear equation, well this is a constant, right? It's a constant 60 minutes, while this is linear to how many gigabytes you have. Does that make sense? And that pigeon's always gonna win if it's anything over 2 gigabytes, so why not just use the pigeon? And that's the story of the reason of why Big O is so important, in that we want to figure out which method's going to be faster, and also how we can make it efficient. So do we want to be able to do as constant as possible, right? Or is it only 1 gigabyte, and we just have to do it once over the internet. Which case do we use what? And there are always different cases for everything. So let's look at an example here. So Java code, we have Java, just 3 print statements. The way we would notate big O notation is that for every single one process that we do in computer science, so a print statement, we count it as 1. So one process is 1. So here, print A, print B, print C would be what? What would my big O notation be for that? It would be 3, right? It's O of 3. So I'd write O of 3 down. Let's look at this while loop here. If I have a while loop, it's a broken while loop. Don't look at it in the context. It happens X times. What would happen with this while loop? How would this while loop, what would the runtime of this while loop be? O of n? Does anyone agree or disagree?
That's right.
Do you think it's right? It is right. But you can also look at it in that there's 2 pieces of statements. So it's one thing here, but each of those is happening 2 times. So yes, O of n, but also you can say like 2n, right? Because it's 2 times n times, right? Or x times. So yes, you're correct. This is another way. I want to kind of go over that example as well, but we're going to use a couple rules to why it is n instead of 2n. So technically this is O of 1 instead of O of 3, and this is technically O of n instead of 2n. And I'll explain the rules in a second, why that is. So the first rule is that different steps get added. So we kind of saw that with print A, print B, print C, where we added them up, in a sense. For this, we have 2 array print methods that are the same, but we have 2 different arrays. So we have 2 arrays A and B. We have 2 different sizes, A and B. We're going to add up A and B together, and that's going to be O of A plus B. So it's O of A plus B. And the reason for that is, what if array A is the size of 1,000,000, but the array of B is 10? You want to include both of them, so that maybe on the other hand, B is 1,000,000 and A is 10. You don't know which one's going to be the bigger one. You want to make sure you count both of them. So that's why we use 2 different steps, add them together. This kind of relates to step 3 as well. I'll come back to that. Step 2, we're going to drop constants. So you kind of did this in that first one with that while loop. We're going to drop constants. So on this side, we have a find minimum equation happening in a for loop, and we have another find maximum happening in another for loop. Here, we're just doing find maximum and maximum in the same for loop. What would the O of n be just for the first for loop here? Or with the big O notation? What would the runtime be for this guy right here? Any ideas?
2n.
You think it's 2n just for this guy? This for loop only.
Oh, just
Just the first for loop.
right.
N. And what would this for loop be?
N.
N as well. Right? We see that? You know, this is running n times or x times, and this is running x times as well. So you're saying 2n for this entire thing, right? Let's look here. We have 2 things happening here, but we have only one for loop. What is this going to be?
N.
It's going to be n, in that it's running n times, but not n plus n times, right? So it would be 2n and n, but we're just going to drop off the 2 because it's the same thing as happening over here, and also we just want to look at the worst case. So the biggest thing in this, and I'll kind of explain it on the next, on the 4th rule, we want to be looking at the worst case of something happening here. So what's the worst, most computational thing? We're going to take that, and that's going to be our answer. So we're going to go ahead and drop that constant, so it's just going to be O of n on this side as well, same as this. And we just drop constants in general. Cool? Does that make sense? So step 1 was we add up different steps. Step 2 was we drop constants. Rule 3 is different inputs get different variables. And I kind of showed this before, in that you have A and you have B, and you want to add those up together. And it's, again, it's the 1,000,000 to 10 size, right? Where you want to add A and B to make sure that they have different constants. So this one would be A plus B, right? Cool. So that's 4th rule kind of encompass everything in what it means, in that we're going to drop non-dominant terms. So like we said before, what is this for loop going to be in runtime?
O
N, right? N. What is this loop going to be?
O n squared.
Yes. Do you guys see why that is?
This one's what?
Yeah. So this is going to happen n times, but it's going to happen n more times. So it's going to be n times n, which is n squared. So what is the overall runtime of this going to be?
N squared plus n.
N squared plus n, right? Or we're going to add up the two different constants. We're going to add up n squared plus n. So I'm going to write it on the whiteboard really quickly. We're going to do O of n squared plus n, right? That's ideally what our answer is. Now, what if I take this and I say O of n squared plus n is faster than O of n squared plus n squared, right? That's true. That's a true statement, right? This has one more n to it. It's going to be faster on this side. But on the left side here, I'm also going to say it's also slower than O of n squared. That's also true, in that n squared is faster than it because it has one less n. But now let's go back over to this right side, where we can simplify this in saying O of O of 2n squared. But what do we do with the constants?
We drop them.
We drop them. So we're going to remove that 2, and that just becomes O of n squared. But also this is O of n squared. So since both of them are O of n squared, there's a squeeze theorem in math, where since this equals this, the middle's got to equal the same thing. In that this is also going to be O of n squared. Does that make sense? And that we're kind of cutting down the runtime. And I'll explain it in a second with the actual code. So if we look on this side now, the actual code, what happens if n is 100 million, right? That means I run this for loop 100 million times. But now this for loop is n squared, right? We said that. We run it 100 million times 100 million. So there's 100 million times 100 million, extra more times. So in comparison, this is what? This is 1/100th million of this guy. So it's tiny. This is like less than 1%, smaller than 1% from this amount that's actually happening here, right? You're thinking real hard.
So that's where the squeeze theorem part applies.
So it applies in that we're just dropping the constant because the amount of computation that this takes is far greater than this. This is insignificant. And that it's tiny in comparison to this. So we just look at the big thing. We look at the worst case. We look at the thing that's taking the most computational power, and it's going to be our double for loop. That make sense? And it doesn't make sense if you look at it as like a 10. If n is 10, it doesn't make sense because you're like, oh, that's a tenth of it. But if you look on the massive scale of 100 million, you're like, dude, it's tiny, right? Cool? So that's why this squeeze theorem works, and that we're just looking at the worst case. We're just looking at the worst case. We're dropping constants. We don't want to look at anything beyond just the worst thing happening. Cool? Cool. So I'm going to erase this real quickly. And the next slide explains this all. I say 200 million. But now we're going to kind of go into sorting. So who remembers their sorting? I know you were doing it 2 years ago, so you did more sorting. But I think the rest of you three might have done bubble. You did merge and recursive merge, right?
I think I
Yeah.
did those two as well.
So you probably did those, but you also probably did selection and insertion,
Oh.
and maybe quicksort as well. So, yeah, if you remember those things, I'm going to kind of go over all of them, but I have examples and stuff like that. But who remembers bubble sort? Yeah, what did it do? How did you do bubble sort?
Nested for loop.
And that's the for loop, but how does it actually work?
Traverses it and swaps numbers if it's less than.
Yeah, so example here. Exactly. So we're going to take an array, and it's unsorted right now, and we're going to take the first two numbers. And we're going to say, hey, is the first number, or is the second number smaller than the first number? Then you're going to swap it, if it is. You're going to say the next two numbers. Is the next number, the second number smaller than the first number? We're swap it if it is. Same happening here. So 5 is greater, or 1 is smaller than 5, you swap it. 4 is smaller than 5, you swap it. 2 is smaller than 5, you swap it. You keep doing this for one iteration. Then you do another pass, and you do the exact same thing. You do another pass and do the exact same thing. You keep doing these passes until you do one full pass where there's no swap that happens, and then it finishes. And it's like, oh, I'm done. I have no changes. This is my final array. Everything else is smaller on the left side of the value. So that's how bubble sort works. So you said you think it's a nested for loop, right? Does that make sense for everyone that it's a nested for loop? And I'll show you the code in a second. In that, yes, you have a for loop. You have another for loop inside of it. It does have the values I and j. We're just going to say any amount of the array size is n. So we're gonna say, hey, array size is n, so we're gonna default this to n in a sense. And it's just to understand what our overall efficiency is. So we're happening, what is my runtime of this program?
N squared.
N squared, right? Does that make sense?
Yeah.
Because it's a nested for loop.
Yeah.
We kind of talked about before where a for loop instead of a for loop is going to run n times n times.
So n is kind of like an iteration.
Yeah, n is just how many times we're happening.
Okay.
N is just like, hey, this for loop's happening n times. The next for loop's also happening another n times, so we're n times n.
I see.
It could be I times j, but we're going to kind of work that in together and say n squared. Because it's both happening for both, it's the same size for the while loop, for the loops. So yes,
I have a question.
yes,
What is this swap?
the
Is that
ampersand.
a method?
This is a method, yes.
Okay.
Someone asked, not necessarily about the swap, but the ampersand itself.
Yeah, I noticed that, and then I noticed the swap. So.
The ampersand is an interesting concept of, if you saw the slide before that's in pointers, that is a topic later down the line where you can access data through accessing the address in memory versus actually accessing the data itself. We kind of talked about it a little bit, but it's an interesting concept, and we'll talk about it more down the line. But that's also cool. So yes, O of n squared because it has two while loops, and that's just the average. Now insertion sort. Who remembers insertion sort? Does anyone remember it? It's okay if you don't have examples, but any guesses?
You're inserting something.
You're inserting something, yes. So insertion sort. We're going to take that first value, and we're going to say, hey, is the item on the left smaller than it? The first one doesn't have anything. So now we get a second value. Is the item on the left smaller than it? It puts it in place. It swaps. And then 2, we say, is the item on the left smaller than it? It is. Is the item on the left that smaller than it? It swaps that one. So it puts 2 all the way at the end. 10. Is 10 smaller than anything on the left? Or, yeah, 10 smaller than anything on the left? It isn't, it stays. 12 isn't, it stays. 1 checks 12, checks 10, checks 4, checks 3, checks 2, and goes all the way to the end. So basically inserting the next value where it's supposed to be along this entire array. But it's doing one value at a time, putting it in the smallest place, and comparing all the way down. So if I asked you to think about the coding for this, how would the code be structured? I'm going to give a hint in that, what does this look like, this chart? Any ideas of what this chart looks like?
2D array.
Yes, it looks like a 2D array. What do we do with 2D arrays? How do we iterate through them? Nested for loops, or nested loops. In that we're both going across to access the different items. So first we're accessing the first one, and the second one, and the third one, and the fourth one, and we're comparing to the left. But we're also going down. And then we're accessing each individual row over and over. So we got 2 loops. We have a for loop, and inside of it we have a while loop. And what do you guys think the runtime of this is going to be? It's a little different because the way it works is that it only checks the first one to the second one to the first one, the third one to the first one, and the second one. And it only checks these ones. But what do you think the overall runtime of this is?
N squared divided by 2.
N squared divided by 2. Not quite.
I thought it was just like similar to like A plus B when you add it because they're different.
Kind of. So we're just going to round up and say worst case. And that it's going to be n squared as well. And yes, there is some weirdness to it in that ideally it's not accessing as memory pieces as bubble sort might be doing, right? But it is a little faster in that it should be n squared, but a little bit less. Does that make sense?
Yeah.
Because it's not accessing, if we go back to that first line, and here, it does this line, but it doesn't access all these things. It doesn't have to go and access these things. Here, we don't have to access anything back here. So we're accessing a little bit less of what bubble sort does, and that bubble sort trims through the entire thing every single time. So yes, it's O of n squared to round up and say, hey, n is the worst case. We're still going to happen n times. Now, selection sort. This is the last sort that I'm going to go over. Does anyone remember what this one is? Cool. If not, let's do it. So selection sort, I have the code and the example here. Selection sort's interesting in that we search through the entire array. We search through the entire array and we find the smallest value. And we take that value and we put it in the 0 place, or the leftmost side. Then we chop our array. We say, hey, let's ignore that first place because we know that's the smallest value. We're now going to search for the next smallest value in our array of 1 to 4 here. it's a 12, we're going to move it to the leftmost value. Now we ignore that 12 and 11. We're going to look for the 2 and 4 place, find the smallest value, move it over to the left. And we keep moving to the left, and we're selecting the smallest item and moving it to where it needs to be, which is the left side. So that's how selection sort works. It's also a little different too, right? In that we're changing the size of the array. So what would the runtime of this be?
Would this also be n squared?
It would be. It would be because it's also worst case as well. And that worst case would be n times n. And it's a little less than n squared, right?
Yeah.
Ideally, it should be a little less than n squared. Does that make sense to everybody? You guys get it? Cool? Now, yes, that's 2 nested loops. Now my question to you guys is, which one's the worst of these 3 that I just showed you?
Bubble.
You think bubble, bubble, bubble? You think bubble too? Everyone thinks bubble?
Yeah.
I think none of them and all of them. And the reason I think that is, they all have their different qualities. In that, say I give you an array that's perfectly sorted. It's got 1 through 10 already sorted. In the best case, bubble sort and insertion sort have O of n, and I'll show you in a second. But selection sort over here, you probably thought selection sort was probably one of the better ones, is n squared, and I'll show you why. And that if we go to bubble really quickly, bubble, it checks, hey, do I swap these 2? If it's a perfectly sorted array, it doesn't swap. Checks if it swaps, checks if it swaps, checks if it swaps. And if it's perfectly sorted, it does that whole check without swapping anything, and it's like, cool, I'm done. It goes through the array list n times, and that's it. It goes through the n list once, that's n times, it's O of n, right? Now if we go to insertion sort. If I have a perfectly sorted list, I check for the first one. Left, it's going down instead of over, like bubble did. I'll check the first one. Does it have anything small to the left? It doesn't. The next one, does it have anything small to the left? It doesn't. It's smaller and smaller and smaller and smaller, and it goes vertically down, but it goes only n times down, right? And that's O of n. But now for selection, what do I have to do here? I have to, if it's perfectly sorted, I still have to say, hey, let's go find out of this entire array the smallest one. So it searches for the smallest one, and if it's on the left side, it still puts it on the left side. Now I search for this side, I still search for the smallest one, but it's on the left side. I still search for the smallest one, put it on the left side. But I'm still iterating through every single value, accessing it and comparing it. So I compare the smallest value, but I still have to go through horizontally through the array, but I also have to go vertically through it. Now I'm checking everything no matter what. So selection sort's the worst for the best style array, right? So if it's perfectly sorted, selection sort sucks. Now if I ask you, which one would you choose if I give you the worst sorted array? Which sorting method would you use?
Selection.
You'd use selection? What would you use? Selection? Selection? Selection. Why did you guys say that? What do you mean by that's the best one? I want you guys to think about these things of why we're using these things.
Doesn't have to go through the entire array every single time.
Yes, so it starts cutting down and trimming the size of the array, so we only have to go through, by the end of it, one value, instead of bubble where you'd go through every single value, or insertion where you'd also go through a majority of the values as well. You're kind of chopping it down. So in different cases, we've mostly been computing average time. In different cases, you use different types of sorting methods. Does that make sense? And that's the big thing I want to kind of get there, is that we're going to be adding more sorting methods. We have to figure out when it's best to use these things. If you guys ever go do an interview, for a coding interview, like you go to Facebook, Microsoft, Amazon, all these big companies, they're going to ask you, hey, can you write this section of code on the whiteboard? You write your code on the whiteboard, and they're going to be like, hey, they will 100% of the time ask you this. They'll ask you, what is the runtime of your code, or what is the big O of your code? And you're going to have to just look at your code and be like, okay, I have a while loop inside a for loop, so that's a nested, that's going to be n squared, but I also have an n down here for this extra for loop and another one. And you're going to define like, hey, overall mine is n squared. Then they're going to say, hey, how would you better this code? How would you make it faster? Is there anything that you guys know that is faster than n squared? N, yes, other than n, sorry. Because it's only sometimes n. Right now, average-wise, it's only n squared of these things we have. You can't choose the best case every single time, right? You might have some job that you're like, hey, I have the majority of this stuff sorted because the teacher's done half of it. Can you sort the rest of it for me? And in that case, I would straight up use bubble or insertion. Probably insertion, right? Because then I know it's majority sorted, so it's going to be faster than selection in that case. But if someone says, hey, how do you make your code faster? Now you can go and say, hey, merge sort. What is the runtime of merge sort? Do you guys remember at all? It's log of n. Where it's log of n, which is between n and n squared. It's not quite either of them. You can kind of then say, oh, I would actually do maybe a little bit of merge sort instead of bubble sort, because bubble sort sucks, right? And you got to kind of understand how to diagnose runtime and also how to better your code. Because if you write code for Amazon, and every single time someone opens up the shop for Amazon on Amazon.com, and they have to go through a nested while loop, they're doing that X amount of times across the entire world. That's a lot of time, right? That's a lot of time and it adds up. So on the big scale of things, you kind of have to figure out, hey, I need to diagnose that instead of being this slow or just doing it because it's easy, you have to figure out, hey, it is good to use this because of this speed it runs at. And then you'll probably have a conversation with another engineer that was like, nah, let's do quick sort instead, it's faster. And you kind of have that back and forth. So I'm trying to get you guys to understand that there are use cases for each of these things. Cool? Does that make sense? Everyone good? Chilling? Big chilling? Understand? Does it make sense? Cool. We'll also go down the line more than just adding these sorts. We'll probably learn more about different data structures. So we know about, I said, arrays and array lists. Ideally, we'll add trees and heaps and stacks and queues. And all these things we'll add to our list, and then we'll figure out, hey, there are good times to use a stack, or there's a good times to use a heap or a binary tree, and that these are good cases to use these. Why would I use an array instead? And ideally, you guys are kind of finding this stuff as we go. There are a couple more sorting algorithms. Did you do quick sort, Peter? You didn't do quick sort. So we'll probably do quick sort in this class. More than just these. Quick sort's probably one of the faster ones. I think there's 3 different types of quick sort now, where it's like quick sort 1, quick sort 2, quick sort 3. It's probably one of the faster ones. There's also shell sort and then radix sort. Radix sort's really cool. In that, have you seen it at all?
Yeah.
What is so special about radix sort? Do you know?
I forgot it, but I saw like an entire video about like sorting methods.
Yeah, we're gonna go over that in a second. So radix sort is very interesting. That just think about it. Radix sort does not do any comparisons. Radix sort doesn't do any less than, greater than, or equal to in its entire sorting algorithm, and it's still able to sort it. Just think about that. It's so weird. How do you do 0 comparisons when you're sorting stuff? It's a cool algorithm. But we'll probably go over that later. But yes, that video. You've probably seen this video.
Yeah.
Who's seen this video? Oh, you guys seen this video?
Multiple times.
Most of the times? All right, cool. We're going to go over it again because then we kind of understand like what's going on here. And that this is going to be a selection sort. So what does selection sort do again? It basically takes an item and puts it to the left, and then it shortens the array, right? So we'll start with the first one, we'll put it to the left, and then shorten the array. And we're only going to see it slowly decrease the axis of where it's accessing, because it doesn't have to access anything else on the left anymore. So let's go ahead and watch it. And have you done it with sound before? Has anyone not done it with sound? You guys have all done it with sound? Oh, it's so much better. Oh, let me check. I need to change my sound output. Dude, this video is too good.
It's amazing.
Is it this guy? No. It's supposed to be, oh yeah, that guy. Alright, we're just gonna play it off my laptop. Oh yeah, did I not change it? There we go. That's what I'm looking for. Alright, we're gonna go back to the beginning. And you see how the red is stopping accessing anything on this left side, right? It's only accessing this stuff because it's shrinking the size of the array. Insertion sort. We take the one, we swap it down until it needs to go down to where its place needs to go. So we swap it down. But it still has to access the entire array, right? Insertion sort's a little slow as well. In comparison to selection sort. Good, buddy. Do you guys have 7 periods?
Yeah.
Yeah, if you need to get out of here, go for it. But that's the entire lecture. That was the end of it. Thank you guys for coming. I hope you guys enjoyed it. This is quick sort. It's kind of like merge where you're splitting what's going on. You kind of sort at the beginning, and then you take 2 chunks and you sort that up, and you take 2 chunks and sort it.
Is this using recursion? Quicksort?
This one, I don't think it is. I don't think it is. I don't think you use recursion for this. It's so satisfying.
But the sounds too, yeah.
Hello. This is merge. You guys all know merge. That's half and half. Hello. Yeah, you guys are welcome to head out. You're welcome to chill for a little bit. I do have a 6th period, but they're coming in as we go, so I'll keep playing this. But thank you guys for coming. If this hope it continues to be interesting. There are exercises that Dr. has used in the past, which I'll probably post for you guys. And I'll post the slides on. Is that cool? Yeah. Cool. Thank you guys.
Thank you.
Yeah. Have a nice day.